Hey, it's Bill Trombley from Trombley Tool in East Troy, Wisconsin. This is video number 11, and this will be part 2 in regards to aluminum heat treating. There were a couple comments that were posted, and I thought I would go through it. One thing that's important to remember, we're trying to have this conversation for metal shapers. We're not looking for PhD level scientific discussion on it. And that's important. And it's important because to go to that depth of discussion, most people wouldn't follow it in the first place. Secondarily, most people don't even care. You know, a lot of guys just want to make parts and have least amount of trouble as possible. So I'm trying to keep it simple, intentionally. Do I have a huge, extensive material science background? I do not. You know, like I had talked about in earlier videos, I have a friend of mine, PhD Mike, who has a PhD in metallurgy. I've spent time with him and had a lot of in-depth conversations. And he says, you know, you're asking graduate level questions with some of the stuff that I'm posing to him. Because it's a subject that could get extremely deep in a hurry. So we're trying to keep that in mind with some of this stuff. Is it going to be simplistic conversation? Yes. But for most, like I said earlier, for most of us, that's perfectly fine. So one of the questions that was put forward by a friend of mine, Bill, and you'll see it in the comment sections, was when you're talking about the Chinese import aluminum, could I explain a little bit more that what did I mean by that as far as the hardness is some guys get the import aluminum and it's different than the old stuff. What I'm trying to convey is in the H number, you know, we had H12, 14, 16, 18, and there are these different level of hardnesses. It's just important to know that that exists. You know, if a guy buys a sheet of 30030 and then he's surprised that the H14 is harder, a lot of people don't even know that the H14 number actually means anything. So all I'm trying to convey is that that actually does mean something. Is it possible that the Chinese aluminum is harder? Sure. The other thing I was trying to convey is that 3003 aluminum is made to an international specification, meaning that the chemicals that were put into it, when you send it out for a metallurgical analysis, it would come back stating this is 3003 aluminum. It's not 3004 or 3002. Is there a percentage of tolerance when the material is built? Absolutely. There's tolerances in everything. So how much percentage of elements that they put in there, could that be off slightly? Yeah, it's quite possible. What makes it hard at the steel mill when they roll it is it's elongating the grain, and that's what makes that assigned hardness number. And I'm going to make a simple demonstration on that here to help kind of get it so people could maybe visualize that a little bit. But there too, there's a tolerance on what is deemed hardness. If you send in a piece of tool steel into the local heat treater and I say I want it to be heat treated to 55 Rockwell, I have to give them a tolerance, you know, 55 to 57 HRC. So is that causing these slight possible differences? Yeah, you know, so hope that helps clarify that. The point is the Chinese stuff not 3003? No. If we took a test coupon and sent it in with an American coupon, I would be surprised if a metallurgical lab, without going into graduate level studies, would be able to tell the difference. Right? If they just did a simple test, they would go, they are the same. So I guess that might help clear that up. The other thing is grain structure. It was said that some of the old guys said that old materials had grains, and is it true that new aluminums do not? That is not true. Aluminum and all metals, for that matter, are crystalline structures, which means that it starts out as a crystal. If you look it up in text, in books like this metallurgy book here, which is the 5th edition, and really awesome stuff in here, crystal is a grain. It's the same thing. So if we're saying crystals or grains, it is in the exact same language that we're using. So does old aluminum have grains to it? Yes. Do new aluminums have grains to it? Yes. And I've actually, and I could prove it, I guess, I have the etching compound here that a metallurgical lab would use, and I etch the aluminum, and I have a high-powered microscope tied into my computer, and you can actually see the grains, which is nerd level kind of stuff, but I love that stuff. So it is a grain structure. So what's important to know, and why is that? And I hope Ray is okay with this. Ray Shaleen has wonderful videos that he's got out on YouTube as well. I think it's ProShaper.com or ProShaper's video series. And he talks about that metal is clay. And for what he's referencing, he's absolutely right. Is the grain structure clay? No. But it actually makes this conversation a little bit easier. So if we have here actual real clay and a sheet of aluminum, then there's a reason why I have the clay here. So when we're talking about grain structure, we're also talking about grain direction. So all the metals have it, aluminum has it, and you can actually see it. If you got, and I don't know how well this will show up in the video on your TV, but you can see the grains line up with my blue line there. So what is that? Well, that's what this is. And this is going to be a very simplistic explanation. So in the steel mill, they have a molten vat of aluminum. They take it, and how do they get that to this? They take the molten vat, in essence, they cast out a bar stock. And I know here too, guys are going to go, dude, this is way too simple. And like I said earlier, yeah, right, that's what we want. But it goes through a rolling process. And this is where the term cold roll comes from, or hot rolled. Because it goes through a roll that looks like this. Now this is a slip roll, right? And any metal shaper knows what these are. But in the steel mill, it's the same thing. It's just on steroids, right? It's super huge. And I saw a video once, I think they cast out an ingot that's like 6 feet long. And by the time, and I don't know, let's say it's 12 inches thick. By the time they're done, they get like 2,000 feet of material out of it. Because each time the material rolls back and forth through it, it gets thinner and thinner and thinner. And that's how they do this. And this is rolling through there like that. And it's squishing it down each time. So you may go, okay, why is that important? This goes to the whole metal is clay thing. So if you were to look at the grains here, it creates this grain direction. Well, when the grains start out originally, they're somewhat irregular, flattened out shapes. Now I'm making them round. Why? Because it's the easiest way to do this. If you want to start seeing pictures, look up aluminum grains on Google. They got photographs and all the really cool stuff. But let's say it's round. So when the bar is cast, the grains are somewhat like this. When it gets rolled, the grains become elongated in the direction that it's rolled, like this. And you go, why is that important? Well, have you ever heard of bend allowance? And we use bend allowance every day in aircraft stuff. And some guys might go, I'm not an airplane guy, what do I care? Okay. But how many of you guys ever bent a piece of aluminum in a sheet metal brake like this and had it fracture? You see the fracture line to the point where it breaks. So what happened? When I bent this, I bent parallel to the elongated grain. When I bent this, I bent perpendicular to the grain, elongated grain that's internal to the material. The other thing I do is I increased the bend radius. Why? If the grains in the material going through the rolling mill are elongated like this, if I bend and it's parallel to it, they break easy. If I bend perpendicular to the grains, what happens? They bend and they don't break. It's kind of a bad demonstration, but you get the point, right? You can see here that the clay would allow it to bend. So you can see now why is there a grain direction and what happens. So there's another question came up about annealing. And that in order for us to do this technically, the Sharpie process is a relieving of work hardening. The true annealing can only be done at a very controlled temperature over a duration of time. Is that technically correct? Yes. What happens in the process of annealing? The grains have been elongated like this. When the temperature goes up, and what they say is we call it annealing. Heat treaters and metallurgists call it the recrystallization temperature. Which means what? Well, what they say is the grains go into solution, new grains form, and they revert back to the original non-elongated size. Is there a lot more to it than that? Yes, there's a ton more to it than that. But it's a simple way of having a simple conversation. Because they go and the grains are no longer elongated, the material is no longer as strong, because what makes material strong is the elongation of the grain. You revert back to the original size, the material goes soft. That's how you get back to the old state. When and you go, what in all of this have to do with metal shapers? Well, us as metal shapers, if we run really high pressure in an English wheel, what am I doing to the grain? I'm elongating the grain in the direction that I'm wheeling it. That's why it gets hard. That's how you work harden it. That's why if you anneal too late in your project and you make the panel soft, you have to now re-elongate the grain. I have to go from this back to this to make it strong. So you can see why it helps to understand this to the level that we need to know as a metal shaper. The question is also, if we torch anneal, are we not, that we are not annealing it? And it's possible. So what I did was, I took a sheet of 3003 H14 aluminum, sheared it in two pieces, torch annealed this. Traditionally, like I showed in the last video, temp stick, Sharpie marker, will hold that, heated it up, let it air cool. Took this piece, put it in the heat treat oven. Heat treated it at 750 degrees for 30 minutes per military tech order number 1-1A-9, which is this really cool book here, Engineering Series of Aircraft Repair for Aerospace Metals, General Data and Usage Factors. This book is awesome, if you care about it. And in here, it clearly states how I should go about the procedure. And I followed it to the best that I could in a hangar in East Troy, Wisconsin. Is this a testing lab? No. Can I make airworthy parts? Absolutely. So once I took the test coupons out, I tested it with my hardness tester. Is this scientific? More scientific than most. Is this scientific like a testing lab would have? No. Could you argue that there's an inaccuracy associated with this? Absolutely. So what did I notice between the two? What were my results? My results come back that they are exactly the same. So the material, when you look in that military tech order, it tells you what the yield strength would be if it was O. And when I test them, they come back as being O. Right? They're annealed. Is there more to it than that? Probably. Does it matter for us? Nope, not at all. Because if I handed this to you, anyone, you wouldn't be able to tell the difference. And as it's metal shapers, you wouldn't be able to notice the difference. The duration of time for the 30 minutes, that's for materials up to and including a 1/4 inch thick. So at what point in the timeline does this 40 thousandths become technically annealed? Is it at the 5-minute mark, the 30-second mark, or the 29-minute mark? I don't know. That would have to become a much more of an advanced conversation than we need or that I'm really willing to do. It's just not relevant for us as metal shapers. So what I'm hoping here is this helps clarify a couple of the questions in aluminum. And now you can see why grain direction matters, why bend allowances exist, and we're still struck with the crystalline structure and things of that nature. And remember, simple for a reason. And I hope you guys enjoy it. I hope it makes sense, and we can move forward from there. So thanks for watching. Remember, there's earlier videos to guys go look at as well. That'll help with some of the language that we're using or whatever. And have a good day. Thanks. Bye.